Video, we're going to talk about inscribed and circumscribed polygons. So an inscribed polygon is a polygon with all vertices lying on a circle. So if I draw a circle and I draw some random shape like this, all of these vertices lie on the circle. It is an inscribed polygon. A circumscribed polygon is a polygon with each side tangent to a circle. So instead I have something like this where I have this is a circumscribed square, I guess. I'm not very exciting. I tried to get that one to touch. So yeah, that would be a circumscribed polygon. We could also say that the circle is inscribed on the square instead, but either one. And incenter of a polygon is the center of a circle that is inscribed in a polygon. So here, circle is inscribed in a polygon. Center of the circle is called the incenter of the polygon. Okay. So there's two theorems regarding inscribed and circumscribed polygons that we're going to talk about today. The first is that if a quadrilateral is inscribed in a circle, its opposite angles are supplementary. And the reason for that is because if we look at two arcs, so like if I look at this, say here, plus this, oh, I drew that way too big, sorry, this, here, let me draw this correctly. So if we look at like this angle, right, the opposite angle is this angle and this angle here. So this angle intercepts this arc, and this angle intercepts this arc, right? Now I know that those two arcs have to add to 360 degrees, and therefore the angles, if we think back to our angle arc theorems, the angle has to be half 360, so it must be 180 degrees, right? Half of 360 equals 180 degrees. So hence opposite angles are supplementary, just because they intercept the entire circle worth of arcs. Second theorem, if a parallelogram is inscribed in a circle, it must be a rectangle. And I've drawn that here for you. So yeah, try it. If you draw like a circle, you'll find that if I draw two parallel lines, right, this isn't, they cannot be a parallelogram unless if you draw it out like, oh man, that's a bad circle, like this, then it's a rectangle, right? So it has to be a rectangle. Now let's apply these. So our first example here is I've inscribed a quadrilateral ABCD into a circle with its center at O, and I want to prove that angle B is congruent to angle ADE, ADE, that one. Okay, so let's do a two-column proof here. The first thing I'm going to write down is that ABCD is inscribed in circle O, and that is a given. The second thing I want to look at is I want to be thinking about the two theorems that I just introduced to you. So if I look at angle B, it is supplementary to angle ADC, right? Because they are opposite. So angle B is supplementary to angle ADC. Theorem number 1. Number 3, based on theorem 1, right? Because they intercept the arcs. That was the whole thing we talked about. I can say that angle ADC is supplementary to angle ADE, right? ADC, ADE, and that is because two angles forming a straight line, have to be supplementary. Right. This plus this has to be 180. So then finally, I can say that angle B is congruent to angle ADE. Right? I can say that because two angles supplementary to the same angle must be congruent. Right? And there we are. We proved it. So yeah, using the supplementary angle stuff just gives you one more tool in your math tool belt to solve problems like this. All right, let's move on to one more example today. So here, I have a parallelogram ABCD inscribed in a circle, and the diagonals intersect at the center E. What must be true about this quadrilateral? Well, you can see if because I've drawn it here, but it must be a rectangle, right? Even if I didn't draw it, you know it has to be a rectangle because they told you it's a parallelogram, and all parallelograms inscribed in a circle have to be rectangles, and that was theorem 2. What is BD? Oh, did I write that wrong? I did write this wrong. What is BC? BC is a diameter, right? It passes through the center. It is a chord. It is a diameter. Okay. If AB is 5 and BC is 6, then find AC. So AB is 5. BC is 6. So this whole thing is 6. Then I want to find AC. What is this? Okay. Well, this is just Pythagorean, right? This has to be a right angle because it's a rectangle. So I can just say 5 squared plus 6 squared equals AC squared. So then AC is going to be equal to the square root of 61. And that's it. So only 2 theorems for that. That's all you're going to have to know. And they're both pretty straightforward, but it's definitely worth practicing. Just making sure you can kind of identify, especially for theorem 1, you can identify that, hey, look, we have opposite angles, so they have to be supplementary. That's going to be the more useful one. Theorem 2 is pretty narrow in what it can be used for. Like if they tell you it's a parallelogram, then it has to be a rectangle. One other thing that could come up is if you're doing a figure inside a rectangle like this, inside a circle like this, and you find out that like AB is parallel to CD and AC is parallel to BD, that tells you it must be a rectangle, right? Because if it's inscribed in a circle and it's a parallelogram, then it must be a rectangle. So that's it. Thanks for watching.